Today we're going to take a look at an application to physics in which we will see how we can apply the theory of integration to compute the work done on performing various tasks. So first of all, we need to introduce this concept of work. So this is work in the sense of physics and classical mechanics. So work is basically a measure of the exchange of energy, and it's defined as applying a force through a given distance. So the main formula is work is equal to F times D. Now, an important caveat, this is only the component of the force in the direction of the motion. So for example, if we have a plane and we have a crate, so let's say we have a crate like this, and we are applying a force to the crate to push the crate or pull it. So we have a force F, and then the crate moves through some distance D. The total work done is the force times the distance. Now, instead, if this force is at an angle, so for example, what happens if we are pulling the tank like this? So we have some force here, and the angle at which we're pulling the crate makes an angle theta with the horizontal. So this is like if you have a rope and you're pulling almost like a sleigh. Now the reason the crate doesn't move up is because there's also gravity acting down, but we're only looking at the component of the force in the direction of motion. So if we think of this right triangle, we have F cosine theta acting in the direction of the plane, and F sine of theta pulling upward. So F sine of theta has to be less than the weight of the crate, because over here the crate has a weight, mass times gravity, so mg. So mg is going to be less or greater than F sine of theta, otherwise the crate would be lifted off of the ground. If you pull too hard, you're going to literally pull the crate up and it will hop off the ground. So we assume that, and if we look at just the component of the force in the direction of motion, it's F cosine theta. So in this case, the work is equal to your constant force at which you're applying times the cosine of theta times the distance. So I'll say F d cosine of theta. So it's only the direction of the force, or the component of the force in the direction of motion. If you press up against a wall for an hour, and you just push as hard as you can against some sort of brick wall, at the end of the hour you might feel like you've done a lot of work, but actually you haven't done any work because the wall hasn't moved. So work is a combination of the force that you're exerting as well as the displacement of the object. So you have to actually achieve some sort of motion as a result of applying your force. And it kind of makes sense, right? Because if I move a box by 1 meter, applying a certain amount of force, I've done so much work. If I moved it 2 meters using the same amount of force but just twice the distance, I've doubled my work. Or if I move it 1 meter but I'm pushing twice as hard on the box to move it that 1 meter, I'm performing twice as much work. So it's a combination of force and distance. Now let's take a moment to think about the units, because units are very important in physics and they can often give insight into problems. Sometimes units alone are good enough to get the key insight to solve a complicated problem. So units of force are newtons. And what is 1 newton? So 1 newton is equal to 1 kilogram meter per second squared. And we know this because force is equal to mass times acceleration. So force is measured in newtons, mass in kilograms, and acceleration in meters per second squared. So 1 newton is 1 kilogram meters per second squared. So kilograms, meters, and seconds are the basic units upon which everything else is derived. So we have 1 newton times 1 meter, so the units of work are Newton meters. So many Newton meters of work. Now that's a new unit, J, which is called a joule. So 1 joule is equal to 1 Newton meter. So basically 1 joule is the amount of energy required to apply a force of 1 Newton through a distance of 1 meter of space. So joules are units of energy. This is energy. Okay, now if we unravel this, well, 1 joule is equal to 1 Newton meter, which is equal to 1, well, a Newton is a kilogram meter per second squared, and then times meter, so it's 1 kilogram meters squared per second squared. Now you'll notice that joules also have the units of kinetic energy. So kinetic energy is 1/2 mv squared. So you have kilograms and then times meters per second squared, which is the same as kilograms meters squared per second squared. So this is indeed a unit of energy. So the final thing to note is that we need to use integration with work problems because we're not talking about just applying the same force on a box across a room. We have stuff that's a slightly more complex going on. So these sorts of problems occur in two types of situations. One is, suppose you have a tall building and we have a rope. So we have some sort of rope hanging down over the edge. So we want to find the work required to pull the rope to the top of the building. So that's the first type of situation. The second type occurs if we have some sort of container. So this could be some sort of swimming pool that has the shape of a rectangle, or it could be something like this. Something that has a shape like that. Or it could be a cylindrical trough. You have some sort of container, or it could be like a spherical container. So you have some sort of container and it's filled with liquid. And you want to take all the liquid in your container and pump it to some elevation. So you pump the liquid out of the container. So how much work is required to do this? Now in both situations, we're doing work against gravity. So when we do work against gravity, the force is just equal to the weight of the object. So the force is actually going to be mg. Because the idea is that you have a piece of mass, and if you lift that mass just at a constant velocity, so you're not accelerating it, you're just moving it upward, the constant force that you'll have to apply will equal its weight because you're counteracting gravity. So that no acceleration means no net force, so the force that you're applying equals out the downward force of gravity, so you're just giving it a constant motion to raise it to a certain height. So when you have water, even in a rectangular tank like this, each horizontal cross-section, let's think of a very thin slice of this tank, just like with volume problems. So everything at this tank is the same altitude. So then we're taking that kind of virtual rectangular shape and taking all that water at the same altitude and moving it all the same height. Of course, the distance that you're traveling depends on what level that slice is at. So a little slice of water, think of the water at the very bottom of the pool has to travel a greater distance than the water at the top of the pool, right? So that's where the integration comes in, because we have to slice it up finely, figure out the work done on each slice, because each slice moves a different distance. And of course, each slice might have a different amount of mass, because we have to look at the area, multiply it by the delta x, multiply it by density to get the mass. So each little slice might have a different amount of mass too, and it might travel through a different distance. So that's where the integration comes from. For pulling a rope or something like this to the top of the building, now it's a one-dimensional problem, but we still have these little slices, and each little slice will move a different vertical distance. So we still have to integrate over the rope to find how much work it takes to pull the rope to the top of the building. So basically for the work problems, we use force is equal to mass times gravity, and of course mass is typically the density times the cross-sectional area times your delta x. So the little mass, delta m, the mass of your slice, is the density at that elevation times the cross-sectional area times your delta x. Just like with volume problems, our delta v was the area times the delta x. We multiply that by density and we get the mass of the slice, and then we have to figure out the distance that that slice moves. as a function of x. And occasionally you might even see rho varying with x, but typically it's common to see rho as a constant. But if rho varies with x, you just replace rho with rho of x, and then you integrate that. So it's always something in this form. For these linear problems, the mass is just lambda times delta x. So lambda is your linear mass density, so kilograms per meter, and that tells you your mass. And lambda also might potentially vary with x. So that's basically a brief introduction to kind of what these sorts of problems look like and kind of the thinking behind it. So then for particular problems, we'll talk about a number of different examples.